Hello, this is Jude Socrates. Welcome to a portrait of linear algebra. Our video for today is entitled Isomorphisms. And that sounds like a fancy word, but we're going to see that it's really about something that you already know. And we are also going to learn how to use linear algebra to solve certain kinds of differential equations. So we are going to learn in our video how to generalize the concept of a bijective transformation, because that's really all that an isomorphism is. So we will use that concept to create isomorphisms between vector spaces. And in the finite dimensional case, when both the domain and the codomain are finite dimensional, we will learn how to use the matrix as usual to decide whether or not our transformation is an isomorphism. And as I said, we will use techniques of linear algebra to finally wrap up everything that we've learned in the last 3 videos to solve certain kinds of differential equations. So let's get the theory out of the way. Suppose you have 2 vector spaces, V and W, and a transformation T from V to W. As usual, we will say that T is bijective if it is both injective and surjective. It's both one-to-one and onto. We will also say that T is an isomorphism, or T is invertible, and that V and W are isomorphic to each other. In the special case when V and W are the same space, an isomorphism from V to itself is also called an automorphism. So of course the prefix auto there, which means self. It's a self-isomorphism. So basically an isomorphism, once again, is just a bijective linear transformation. Okay, so what did we learn in our last video? We saw that if a transformation goes from a lower dimension to a higher dimension, that transformation cannot be onto, but if it goes from a higher dimension to a lower dimension, it can't be one-to-one. So if you have an isomorphism of finite dimensional vector spaces, then there is no choice. The 2 spaces must have exactly the same dimension. Now, what might be a little bit surprising is that the converse is also true. If V and W are finite dimensional vector spaces, and they have exactly the same dimension, then you can actually create an isomorphism T from V to W. So these 2 directions, forward and backwards, can of course be put together into a single theorem that 2 vector spaces V and W are isomorphic to each other if and only if they have exactly the same dimension. So this is the big theorem that you are going to prove in one of the homework problems. Alright, so I hope you remember that back in section 3.6, that was the first time that we combined the concepts of injectivity and surjectivity to create bijective functions, and in particular, bijective transformations from Rn to itself. Okay, so this general theorem can again be tailor-made for linear transformations between abstract vector spaces. So a linear transformation T1 from V to W is an isomorphism of vector spaces. In other words, it's both injective and surjective, if and only if we can find another unique linear transformation, T2 from W back to V, which we call, as usual, the inverse of T1, such that T2 is also an isomorphism, and for all V in the domain capital V, and all W in the codomain capital W, the composition T2 composed T1 of V takes you back to V, and T1 composed T2 of W takes you back to W. So again, this is a good reason why a bijective function is also called an invertible function, because we can construct this inverse. So in other words, the composition T2 composed T1 is the identity on the domain V, and T1 composed T2 is the identity on the codomain W. So we did not have this in section 3.6 because our operators went from Rn back to Rn. So now we are not requiring that the domain and codomain are the same. They just have to have the same dimension. Okay? So again, we write T2 as just the inverse of T1. In particular, by the uniqueness property, T2 must be the linear transformation so that from all W in the codomain, T2 of W is V, where V is the unique vector from the domain such that T1 of V is W. Okay, so quick review. The surjective property tells us that there has to be at least one vector V in the domain so that T1 of V is W because T1 is surjective. But now by the injective property, that V is unique. So there's only one of them. And so we can define T2 of W to be this unique vector V. Okay? Icing on the cake. T1 is also, if T1 is invertible, then the inverse T2 is also invertible. And furthermore, the inverse of T2 has to be the original transformation, T1. Okay, so again, it's just like section 3.6. So that's why we say that T1 and T2 are inverses of each other. So in particular, if T1 is an automorphism, it is a bijection from V to itself, back to V, then now we can say that the composition T2 composed T1 as well as T1 composed T2 has to be the identity function Ising. So again, as before, this notation T1, T2, it's not a very natural notation. So instead of writing T1, we are just going to write T, and for the inverse, we will use T inverse. So a linear transformation T from V to W is an isomorphism if and only if we can find another unique linear transformation, T inverse, from W back to V, the inverse of P, so that for all V in the domain and all W in the codomain, T inverse composed with P takes V back to V, and P composed T inverse of W goes back to W. Again, in other words, T inverse composed T is the identity transformation on V, and T composed T inverse is the identity transformation on W. Okay? So in particular, T inverse must be the linear transformation so that for all W in the codomain, T inverse of W is V, where V is the unique vector from the domain, so that T of V is this W. Furthermore, if T is invertible with inverse T inverse, then T inverse is also invertible, and T inverse inverse gives you back T. Sounds just like something you saw all the way back in chapter 0. X inverse inverse takes you back to X. So thus we say that T and T inverse are inverses of each other. So here's the diagram. Let me scroll down just a little bit. So the composition of T with T inverse goes this way. T takes V to W, and T inverse takes W back to V. So if you take the composition T inverse composed T, V goes back to V, and similarly for T composed T inverse, W goes back to V. Alright, so now let's concentrate on transformations where the domain and the codomain are finite dimensional spaces, so we can talk about a matrix for these transformations. So suppose that T from V to W is an isomorphism of finite dimensional vector spaces. By the last theorems, we know that the dimension of V and W must be the same. Say they're both n dimensional. Then there exists a T inverse from W to V, such that the composition T inverse composed T is the identity on T, and T composed T inverse is the identity on W. If B is a basis for the domain, and B prime is a basis for the codomain, then the matrix for T with respect to B and B prime has to be an invertible n by n matrix. And furthermore, the inverse of T has a matrix with respect to B prime and B, and this matrix has to be the inverse of the original matrix for T with respect to B and B prime. Okay, so this is just like what we saw back in, I believe, 3.7. Okay, except of course we were talking about standard matrices at that time. Okay, now we also have to worry about the bases. Okay, so in our original transformation, the domain is V, the codomain is W. So the bases are written in the order B, comma, B prime. Okay, now that you have the inverse, the domain is now W and the codomain is V, right? Right there. So therefore, the order of the bases has to be B prime first, followed by B. All right, and in particular, if your T is an automorphism from B to B, then the matrix of T inverse with respect to B, okay, where again, we are encoding the matrix with respect to the same basis for the domain and the codomain, then the matrix for that inverse isomorphism with respect to B is just the inverse of the original matrix for P with respect to B. All right, so now we can do examples. So, all the way back in section 5.1, we constructed this function space, W equals span B, and B is made of the three functions, x squared e to the minus 3x, x e to the minus 3x, and just e to the minus 3x. And we created this so that it is preserved by the derivative transformation. So that makes B an operator from W to itself. In other words, the derivative of each of these functions is again a linear combination of these functions. So let's review. The derivative of x squared e to the minus 3x, the coordinates are found in the first column. So it's negative 3 x squared e to the minus 3x plus 2 x e to the minus 3x. Third coefficient is 0, so that third function does not appear in the derivative. Okay, so I was teasing you in the last video when we found the matrix for the derivative, and then we saw, okay, let's talk about the kernel and range. And for that, we said, okay, let's look for the REF, and it's pretty easy to see that you're going to get leading ones here, so you'll just get the identity. Okay, so we knew instinctively that that matrix is invertible. So now let's see. Compute matrices inverse. Yep, it's invertible. No complaints from Maple. And that is the inverse. Okay, so what is this inverse good for? So this is basically saying, okay, this operator from W to W is both one-to-one and onto. It has an inverse. This is the matrix for the inverse. Okay, but what does this inverse mean? Okay, so let's think about the circle made by those transformations. Okay, if you apply D and then the inverse transformation, it takes you back to where you came from. Okay, so what is the reverse process of the derivative? I think we know it as the antiderivative, also known as integration. Okay? So in this case, it's the indefinite integral. Okay, so for example, how can we find an antiderivative for the first function, x squared e to the minus 3x? Okay, so all we need is a linear combination of these three functions that will transform under D to x squared e to the 3x. Okay, so an antiderivative, yeah, what does it mean? An antiderivative for f of x dx is a function, capital F of x, and yet usually we put a plus c there, so that if you take the derivative, f prime of c of x, we will get the original function, f of x. Okay, that's the meaning of the antiderivative. Okay, so how are we going to get the antiderivative for this? It is already hiding in plain sight in our column 1. Why is that? Okay, what is the nature of the inverse? If you multiply a matrix to its inverse, of course, what do you get? Identity. Okay? But now what's the meaning of this? That 1, 0, 0 is what happens when you multiply D by the first column. Okay? But that 1, 0, 0 stands for 1x squared e to the minus 3x. No x e to the minus 3x. No e to the minus 3x. It is just x squared e to the minus 3x by itself. That's what it means. Okay? If you don't believe me, I don't blame you. Let's make a copy of this. If you just multiply by the first column, big review. Yeah, you just get 1, 0, 0. Okay? So this tells us that the antiderivative, or rather, to be more precise, an antiderivative for x squared e to the minus 3x dx is the linear combination. So let me copy all of this down. Let's put some space. There you go. So I will need negative 1/3 of the first function minus 2 over 9 of the second function minus 2 over 27 of the third function. There you go. Now, it's our responsibility to put the plus c as usual. Okay? So, yeah, if you don't believe me, again, why should you trust me? Would you trust Maple? Let's see. Will it find an antiderivative? Compute calculus integration. Oh, you know what? I'm sorry. I don't need that. I just click equals. Oh, there it is. Oh, it factored it out. Compute, expand, and minus 2. Okay. Oh, there it is. That's the first term over there. That's the second term over there. That's the third. Maple doesn't put that silly plus c. It assumes we're intelligent enough to do it. Okay? So the great thing about this matrix that we found, this one, good thing I didn't erase it, is that it can help us find more complicated antiderivatives. Okay? How would you find the antiderivative of, what if you had 7x squared e to the minus 3x minus 4 what's our next one? X e to the minus 3x plus 9 e to the minus 3x. Okay, and once again, we're doing magic here. If you were back in calculus, you would have to do integration by parts several times. That'll take you about maybe 15, 20 minutes. What are we going to do? Well, all we have to do is, 3 steps. Remember the 3 steps? Encode, multiply, decode. Okay, so step 1, encode. Put the coefficients in the correct order. 7, -4, positive 9. Step 1. Step 2, multiply. So multiply, ooh, that's the answer. Okay, so now we can decode. Thus, this antiderivative has to be, let me erase that, and this, and all we need are these coefficients. -7/3 x squared equals minus 3x, -2/9 x equals minus 3x, -83/27 e to the negative 3x. That's it, plus c. And again, you don't believe me? Then come over here and click the equals button. Again, it factors it. Compute, expand. Yeah, that's this term. Yep, that's the first term. Yep, that's the third term. Exactly. All right, so now we get to put together everything we learned today with everything that we learned in the last 3 videos. We are going to find a solution to an ordinary differential equation. So first of all, what the hell is it? So suppose that x is your independent variable and y is a variable that depends on x. Okay, so in other words, y is a function of x. Okay? An ordinary linear differential equation, or ODE, is an equation of the form c sub n nth derivative of y plus c2 second derivative of y plus c1 first derivative of y plus 0 times y equals some function g of x. Okay? So of course these c sub 0 through c sub n, they're coefficients, they're scalars, and n is some positive integer. Well, we are not going to find all the solutions to a differential equation that looks like this, because that's something you would do in a full semester's or quarter's worth of differential equations. Okay? What we will do is just find one solution. A solution to such an equation is a function y equals f of x defined on some interval I that satisfies this differential equation. So if you plug in y and its derivative in here, or f of x and its derivatives over here, you should get the function g of x. Alright, so for our final example, chapter 5, let's put together matrices that we did in the last couple of sections. We are going to find a solution y equals f of x to the differential equation 4y double prime plus 9y prime minus 11y must be 6x squared e to the minus 3x plus 52x e to the minus 3x minus 75 e to the minus 3x. Okay? So of course, that right side is very special. It's from the function space that we created from these 3 functions. Okay? So, of course, in practice, right, you are going to have to start from scratch. If I gave you something different on the right side, you will have to create the function space, make sure that all the functions there have their derivatives, which are also in that function space. Then you will have to find the matrix for the derivative. And then if you have a second derivative, you will have to square that matrix to find the matrix for the second derivative. Okay? But we already worked for these 2 matrices, right? So now we're going to use them. And Yeah, I usually say, if I'm not blah blahing away, this can be done under 1 minute. But of course, I'm going to explain the steps. So, what are we going to do? Well, think of the left side of this differential equation as a transformation. Okay? What is this transformation going to do? It's going to take a function from W, multiply it by -11, take the derivative of that function, multiply it by 9, add these two together, then finally take the second derivative of that same function, multiply it by 4, and add it to everything else. Okay? So that is supposed to give us this linear combination. Okay. So what's going on here? So we can think of T as a linear transformation made of 4 of the second derivative, okay, plus 9 of the first derivative, minus 11, what's the y? Okay, so y, don't do anything to y, leave it alone. What is that? Identity, the identity on W. Okay, so we are looking for, find an f of x. Okay, so do I have an f of x here? Yeah, find f of x here so that t of f of x must be this function on the right. Okay, well, how do we find that function? If only the t were on the right instead of on the left. We're solving for f of x. Well, what did we say? If t is invertible, and of course that's a tall order, then we can apply t inverse to both sides of this equation. So t inverse of this, the left side, has to be t inverse of the right side. Oops, sorry. Try it. There you go. That's better. A little bit cranky sometimes. Okay, so if we can make sure that this transformation is invertible, we're good. We're good to go. All right, so why don't we do that over here? How will we know if it's invertible? Easy. Let's find the matrix. The matrix of T with respect to B will be the matrix of, what is that? The matrix of this linear combination with respect to the same basis. Okay, but remember, the process of finding a matrix for a linear transformation is itself a linear transformation. So we can distribute this out. Okay? Feels like we've done this before. So this will be the matrix 4 times the matrix of B with respect to B squared. Oh, look, we already have that here. Plus 9 times the matrix of B with respect to B. Oh, it's right over here. Minus 11, the matrix of IW with respect to B. Huh, what is that? Well, the identity doesn't change anything. Okay? So this will go to itself, this will go to itself, this will go to itself. So what will be its coordinates? 1, 0, 0, 0, 1, 0, 0, 0, 1. Sounds familiar? That thing, of course, is simply the identity matrix. The 3 by 3 identity matrix. Ooh, excellent. So, we have our ingredients. Take 4 of the second derivative, right there. Let's make some more space. And then we have 9 of first derivative right there, minus 11 of the identity. So I prep an identity matrix over here. There we go. Okay, so keep your fingers crossed. Boom. Okay. So that is an invertible matrix. Okay? So I did make sure that the coefficients here will give you an invertible lower triangular matrix. How will we know it's invertible? REF should be the identity. So notice that the numbers are all the same in the diagonal. Okay, so they're all the same number here. Would be nice if they were ones, right? They don't have to be. Just make sure you can get those ones when you do your REF, your Gauss-Jordan. I can divide by -2, -2, -2. I'll get my 18. Okay. Is there a way that you won't get an invertible matrix? Yes, of course, that's possible. For example, so let me say this, okay? We have 36 minus 27, that's 9, minus 11 gives you the -2. So if we have 9 minus 9, so that will also a -9. Then, oops, we got a problem. Okay? So obviously this technique that we're using only works if this transformation is invertible. Okay? If it's not invertible, then you will learn in your full semester's differential equation class, there's something you could do. Okay? And it involves enlarging the space just a little bit, right? If you include x cubed e to the -3x, now you got a 4-dimensional space. Do you have any hope of creating a 4x4 invertible matrix with these coefficients and the fourth matrix? Okay, but fortunately, this transformation is invertible. Okay, so it was 11. There you go. So it's not confusing. Let's take that. Okay. But it's not important because we're now ready to solve the differential equation. Okay, we have t inverse of this to be our function f(x). So again, if you simplify this left side, you will get just f of x. Okay, so now that we know that this matrix is invertible, how are we going to find our f of x? We need to find its matrix, the inverse, and there it is. You will have -1/2. Then, once more, you got 3 steps. Encode, multiply, decode. Okay? So, step 1, encode. Let me borrow this. 652 and -75. Okay? So, step 2, multiply. Click. Ooh. Alright, so I'm not going to lie to you, okay? I picked these numbers so that we're not going to get fractions in our answer. Let's end with a beautiful answer, okay? So this is our function. Thus, our solution, or a solution to the differential equation could be. So f of x will be, now we get to decode. Okay, so we will get -3 of the first, plus 19 of the second, and then minus 107p of the, okay? Now, unlike integration where we reflexively put a plus c, you don't do that to ordinary differential equations because that will mess up your right side, essentially. Okay, so bottom line, if you take this function and do all of this to it, multiply it by minus 11, find the derivative, multiply by 9, find the second derivative, multiply by 4, add them all together, you should get this as your final function after all the dust has settled. All right, so that's it. And yeah, that is, of course, one of my favorite parts of linear algebra because it brings together everything that we have learned about vector spaces, linear transformations, matrices, matrix inverse, and so on and so on. So I hope you enjoyed that video. I hope you remember this when you take your differential equations class, right? So this is Pete Socrates saying goodbye, and until our next video, there is more to come. I hope you enjoy the rest of it. Bye.